Now let's see, we can then derive the finite element from this weak form pretty much the same way, except for that when you get from this weak form to ax equal to b, you see naturally that this A of ug is going to become my matrix A times u, and my L of G is going to naturally become my right-hand side B. Okay, so this is done by doing the following. So we are first going to represent U as a linear combination of UI times HI, where H is, again, the same basis function I used before. And then I'm just going to choose the G as one of these basis functions, HJ, right? So my A of UG is going to become, and by the way, if you look at the form of A is linear with respect to U, which means if I have U1 plus U2, my A of U1 plus U2 comma G is going to be equal to A of U1G plus A of U2G, right? So by linearity, I can pull this summation out of this A. So this is going to be equal to summation of UI times A of HI HJ, because G is now HJ, right? My L of G is simply equal to L of HJ by simple substitution. Yes?
What's the difference between U and UI?
Okay, a UI is a number, U is a function, UI is a number. UI is a linear combination coefficient in representing the function U as a linear combination of the basis functions.
And is G in X, is that, I forgot if that was like the basis from last class, the X, big X?
Which G?
The big X, is it the set of functions?
Oh, this one? Right, this one is actually a space that is bigger than the finite dimensional space we chose before. So there are two levels of X we are talking about. So here, for example, G only needs to be differentiable one time, right? Because we need a dg dx, but it can still be infinite dimensional. So this is before we make any finite element approximations. And when we go to the blue notation, that is when we go to the finite element approximation and apply the finiteness onto all these linear spaces. So when we start doing the blue math, what we're doing is we now restrict U into a finite dimensional space. We also restrict G into the same finite dimensional space. But when we are deriving the weak form, G actually can belong to an infinite dimensional space. For example, the space of all differentiable functions. Okay, so once we do that, we can see that this weak form now becomes summation of A HI HJ times UI plus L of Hj is equal to 0 for I goes from 1 to n, and j has to be equal to 1 to n. So this naturally becomes AU plus B equal to 0. All right? Make sense? And this A, the matrix A, Ij, is basically equal to the same we call bilinear form applied to Hi and Hj. So this A is what we call a bilinear form because it has two arguments. That's where the bi comes from, right? A can be applied to U and G. And it's bilinear, which means it's linear with respect to both arguments. So if you the bilinearity applies in the sense that if you take A of U1 plus U2, G is equal to A of U1G plus A of U2G, right? And A of let's say lambda times u1g is equal to lambda times a of u1g. So this is clear from the definition. If you have a different differential equation, you need to derive a bilinear form that also has the same kind of linearity. So this is linearity with respect to the first argument. You also need linearity with the second argument g. And you can see this is true for the Poisson's equations weak 4. All right. And this L is a linear form. It's a linear functional. It only has one argument g, and it has to be linear with respect to that. Questions so far? Okay. So now let's start to look at